figure below is a full-scale diagram showing the rest position and the actual positions of a series of particles through which a sinusoidal longitudinal wave is passing from left to right. Describe the movement of a single particle. Okay, every single particle on the wave is oscillating in simple harmonic motion about their equilibrium position. Describe how the compressions and rarefactions move. Since the wave is traveling from left to right, the compressions and rarefactions move from left to right. Measure the wavelength from the diagram. This is a full-scale diagram, so the wavelength can be measured directly from the diagram. The wavelength is the distance between two consecutive rarefactions or two consecutive compressions. So in this case, these are the two compression, so this is the wavelength lambda. So these are two rarefactions, so this is also lambda. You can take from either one of them. Sketch the displacement versus position graph for points along A and B for this longitudinal wave at this instant. So let's say this is A and B. Now the position and the displacement, we'll do a table of values. So at time position at 0, the displacement is 0. At position number 1, the displacement is minus 0.34. This is arbitrary, just measure from what I see here. At the position number 2, so let's say there is a 2 mm away, so the displacement is this value. To the left means that it is negative. Position 3, this is the value. Position 4, this is the displacement. So 5, this is the displacement, and 6, the displacement is 0. So from the table of values, we can make a plot of a displacement versus position, join all the dots, and we have a relationship between displacement and position. Consider the particle at A. Sketch its displacement versus time graph, taking time t equals 0 to be the instant shown. Label clearly on your graph the period t. Now, since the wave is progressing from left to right, a moment later the displacement of A will be that of the particle to its left at the current moment. So now A is here, the one on the left is displaced to the right of its equilibrium position. That means that A will be displaced to its right a moment later. Similarly, the particle of left of A will have a more positive displacement at the next moment. So this particle will have a larger displacement during the next moment in time. Given that the particles are moving in simple harmonic motion, their displacement would therefore vary sinusoidally with time as shown below. So this is the value. So A times 0, next moment it will start to move up. So that's what the graph will look like that. So this is a sine graph.